Has something been going on? What have I missed? I used to do serious science. I was working in artificial intelligence in the 1980s and then doing Bayesian methods for clinical trials and Bayesian computation and all that stuff. And then I got bored with it. And I was really lucky in 2007 to be funded by David Harding, a friendly billionaire. Career advice for all young people: find a friendly billionaire who will then let you do what you want to do. And what I wanted to do was to work on public engagement. So I started making TV programs with Hannah Fry doing climate change. And I did Tails You Win, which sometimes, if you're really unfortunate on a long-haul flight, you might find is you're forced to watch. So, I did the Wipeout course in Argentina. More of that later, if you wish. And I even got on Desert Island Disc. So, after work on COVID, so things have been going quite well as doing public communication. And I wrote books. These two, the Artostats, these are Pelicans, and they've done really quite well. Artostats has done very well. I've even made some money out of writing books. Honestly, this is unheard of in science. Really, because I had made a habit of writing popular books. And then I wrote a popular book. It's amazing. And now I've got this new one, Art of Uncertainty, available from all good booksellers and on the table outside. And that contains all the stuff I've been interested in for 50 years. 50 years I've been interested in probability and what it means, how it operates in the world, about, as you see down there, luck, randomness, predictions, risk, deep uncertainty, all that kind of stuff. There's rather a lot in there. It's a bit, people do say it can be a little bit heavy going at times. So if you do get it, skip the bits you don't want to read. So I'm just going to pick on some of those things today, and things that I can perhaps work with the audience on a little bit. Okay. So what is uncertainty? I like this title. I stole this from somebody. It's the conscious awareness of ignorance, and what that does is put the idea firmly on you. It's a relationship between you and the outside world. You have that uncertainty. You own that uncertainty. It's not necessarily a property of the outside world. I'm not going to talk about whether the world is actually deterministic, even at whether it's at a subatomic level or the non-subatomic, or whether it's all sort of a clockwork universe or not. I don't care whether there's free will. No, it's in the book a bit, but that's not what I'm going to talk about. Because, crucially, that even if what happens in the world is all God's will, or all, the goddess Fortuna, or whatever, I don't care, because the crucial thing is I don't know. I don't know what's going to happen, what's happened, what's going on. Actually, I don't know very much at all, it makes you realize. So, because we may be ignorant about all these things, about the future, about the past, and why things happen, the causes for stuff, which I talk about in the book. So it's a relationship between you and the outside world. So here we've got an example. I've got a coin, I'm going to flip the coin. What is the probability this will be heads? 50%. Okay, we're going to flip the coin, cover it up. What's your probability that this is heads? Come on. Yeah, you're a bit slow. Come on, you're so grudging. You're all very cocky with the 50-50 to start with. Come on, what's changed? You still don't know. It's 50-50. Okay, what is your probability that this is heads? Yeah, 50-50. You got it. Yeah, well, unfortunately, of course, you're completely wrong. Would you have a look at that coin? Turn it over, and you spot that it's got two heads, which is very useful indeed. It's a beautiful, strictly illegal £2 coin with two heads. So first of all, that shows there's many lessons in that little exercise. What I've done is shift from, before I flipped the coin, there was what's called aleatory uncertainty, chance. You couldn't know what it was going to be, because I knew what it was going to turn up, but you didn't, and so you confidently said 50-50. After I've covered up, that uncertainty has changed. It's now become what you don't know, epistemic uncertainty. It is either heads or not, but you just didn't know. You were speaking like and even if I did, you didn't. So it's again, it really is, it shows it's a relationship between you and the outside world. And then when I show it's got two heads, and you were wrong right from the beginning, even to say 50-50, what that shows is that any numerical probability that you use, or anyone uses, is based on assumptions. And your assumption was to trust me, which is extremely rash, and I hope you won't repeat. So that's... This idea of trying to deconstruct uncertainty is what the book's about, and about what this talk is about. How to think slowly about not knowing. And crucially, it is not knowing, it's a subjective, completely personal relationship with the outside world based on our assumptions and our knowledge. Okay, I'd like to talk about what can go wrong when we talk about uncertainty. Because we're used to in our daily lives saying, oh, this might happen, this could happen, this is likely to happen. This can be really dangerous, as this example shows. Some of you may remember the bear. How old are people here? Yeah. Oh, God, there are some pretty old people here, yeah. Some of you may remember the Bay of Pigs, the Cuban Revolution in 1959, when Castro took over Cuba, and then the CIA organized an invasion of Cuba at the Bay of Pigs. I've been there, it's a lovely place, by 1,500 Cuban exiles, and didn't tell anybody, didn't tell the US military. The president knew, but there was Eisenhower at that point, and then President Kennedy found out about it after his inauguration. That's the first he'd heard about it. And he thought, wow, this seems a strange idea. And he got the Joint Chiefs of Staff to do a report on whether they thought this was going to be a good idea or not. And they thought it wasn't a very good idea. And they said, they thought to themselves there's about 30-70 chance of success. In other words, 70% chance of failure. It wasn't a very good idea. However, unfortunately, by the time this got to a report that went to Kennedy, this numerical assessment had been replaced by the phrase, a fair chance of success. What? And, Kennedy approved it, and I'm sure this wasn't the only reason he approved the invasion, because there was this whole groupthink idea that this must be a good idea. And, of course, it was a total fiasco. There's Castro actually jumping off a tank at the Bay of Pigs himself. And they're all captured or killed, and it actually pushed Cuba further into the Russian sphere. And the next year, of course, we had the Cuban Missile Crisis, and perhaps the closest we've ever come to nuclear war. So this was a disaster in terms of communication. But the intelligence services have learned from this, that they've learned that words can be so easily misunderstood, words like likely, could, perhaps. And so we should at least roughly define what those words mean. And in many areas, in climate change and other things, that's happened, that likely is given a definition. So, for example, in the UK intelligence services, if you say likely, MI5, MI6, etc., you mean between 55 and 75% probability. And the way I remember this is that I gave a talk at MI5, and they gave me a mug. It's like those T-shirts. I gave a talk at MI5, and all I got was this lousy mug. But it's great, because what it shows, you need a refill, and you see so it's 55 to 75% empty. You get it's likely or probable. But look, if you look up the top, you can see that 25 to 35% means unlikely. So the Bay of Pigs report, they would have had to say, we think this is unlikely to succeed, which would have been perhaps at a great advantage. So hopefully intelligence services have learned. And in fact, one way we know they've learned is if we look at the decision in 2011 when the intelligence services had thought they'd identified Osama bin Laden in this compound in Abbottabad. And Obama had to decide whether to send in, I think it was the SEALs that went in, to kill him, essentially. And but this was a major risk. And so he did two things. First of all, he set up multiple teams to examine the evidence, multiple independent teams. And secondly, they had to come up with a probability that Osama bin Laden was in the compound. So really, it's fantastic use of intelligence. So Obama is later reported as saying some thought it was only a 30 to 40% chance, others thought it was as high as 80 to 90%. Now, the 30, 40%, we could consider perhaps they were a red team. The red team is a group of people who deliberately, because they're miserable sods, they're deliberately there to look at what can go wrong. They take a pessimistic view. The Ministry of Defence have got a red team handbook you can download. It's hugely recommended for thinking within the defence services in this country, that we should have a group of people who are trying to counter the optimistic groupthink that other people might have. So anyway, in the end, long discussion, Obama said this is basically 50-50, because he had these multiple groups around him. He approved the raid, and he was right. Now, it's been argued since then by some people whether the intelligence services all the different groups should have got together beforehand and come up with some composite view to give to the decision maker. I would strongly say that would be an error, a really bad. The decision maker should know that there's essentially disagreement between the different groups, that between his advisors don't agree. He should know that, because a major source of the uncertainty of the decision maker is the variation in the advice he's been given. And I think a really good example of where that was done was during the COVID pandemic in this country. Remember that good old R number? Oh, yes. One could almost feel nostalgic for that, couldn't one? Yes. Yes, I know. It was so reassuring, 1.3. And what that means is that on average, someone who's infected would infect 1.3 other people. If it's above 1, the epidemic is still going to grow. Less than 1, it's going to drop. Okay, so very early on, the SPI-M group, the advisors, there were 8 different statistical teams around the country, one in Cambridge, all over the place, all trying to estimate R. In fact, there had 12 different models. Some had multiple models. And all using different methods. Some were using sort of deterministic, differential equation methods. Others were using agent-based methods. Others were using purely statistical curve-fitting methods. Everybody was trying their different method. And then they all got together every week online, and everyone look at those sort of results. Look, there are 12. Ignore the grey ones on the right, but the coloured ones in the middle. Look at the variation in the estimates. Now, they all produce their measures of uncertainty, which don't even overlap most of the time, so they can't all be right. Now, think how terrible it would be if we only had one team doing this. We could be grossly overconfident about the estimate, because every model that you use in statistics does, every estimate of the error, assessment of the error around the estimate is based on assumptions. It's based on assuming the model is true. And the one thing we know is the model isn't true. All models are wrong. So all those intervals are grossly optimistic. They're too narrow. In fact, anyone who does any statistics ever, and I've done a fair amount, every single interval you calculate is always too narrow, because it's based on the assumption that the model is true, and it's not. So, we've got to really have some humility about these nice little calculations, the stuff that comes out of the statistical packages. Anyway, the point is that, bless them, they got together and they produce a composite estimate that then is announced to all of us. And we say, thank you very much. But even better, they didn't just do that and produce the composite. They published their individual results. That's in public available data, which was there for everyone to see, which I think shows enormous integrity and just how science should be done. Because it's expensive, because it means that when you want to answer a problem, you set multiple independent teams to try to solve the problem. And that is expensive. It happens in climate modeling as well. Again, I believe that climate modelers shouldn't speak to each other. They really should be doing independent models in order to get an idea of what the variation that you might see that you see. So there's some real lessons there, I think, for the whole idea of what's known as mandated science. Mandated science is when you're forced to try to give an answer, no matter how bad the information is. And I've had to do that in numerous public inquiries in infected blood and so on, where you have to try to answer a question where you don't want to. And actually, I learned a lot from that, because when we did the analysis for the infected blood inquiry, for some analyses, like how many people got HIV because of infected blood, we could be fairly confident about the analysis. And we said we got a high confidence in our analysis. We gave an estimate. But for others, how many people got hepatitis B because of infected blood, we refused to answer. So we were asked to do that, and we said, we're not going to try to answer this question. So you may try to mandate us. No, we cannot. The evidence is so poor, we're not even going to put any numbers on it, because otherwise you might believe them. And then we've got low confidence. And what that showed to me, again, is the value in those situations where science is, where you're almost forced to do the science, of being able to express your overall confidence in what you're doing and your basic understanding. It's enormously valuable. It's very liberating, because you say, "Whoa, I'm not going to say, sorry." No. It's just not good enough. Fantastically liberating. Okay, so the point is, I'm arguing for the value of probabilities. And these can be just subjective probabilities, just judgment. Those Obama probabilities, they didn't come from a statistical model. These were corporate judgments of groups of people. And I think they're subjective, they're constructed on the basis they're not true in any sense, but they're really valuable. And I want to try to demonstrate this to you by giving you a little quiz. Now, what I'm going to do, I'm going to find out how ignorant you are, and whether, not even how ignorant, I want to know if you know how ignorant you are. Do you know how ignorant you are? So I'm going to give you a set of questions, and you're going to say whether you think, quietly, don't shout them out. Oh, and also, no cheating, no phones, I'm going to be watching, no Wikipedia. So I'm going to ask you a set of questions. It's going to have answers A or B, and you're going to say which one you prefer, and then you think about how confident you are in the answer. And you may be 10 out of 10 confident, or you may be just 5 out of 10, which means you haven't got a clue. You just don't know. And then I'm going to tell you the correct answer, and you score yourself. And that's the scoring rule. Okay, so if you say 10 out of 10, it's A, and it is A, you get 25 points. Pretty good. If you say 10 out of 10, it's A, and it's B, you lose 75. Yeah, it's really vicious, this one. It's really vicious. It's like a teacher, if you do well, says, oh, yeah, it's all right. And if you do badly, comes down on you like an absolute ton of bricks. But there's a reason for this asymmetry in scores. I'll explain in a minute. So if you said 7 out of 10, if you're right, you get 16. If you're wrong, you lose 24. Now, you may want a pencil and paper, but you're also clever. I'm sure you can do your running totals in your head. Okay, first question. Which is higher? The Eiffel Tower or the Shard? No, don't shout it out. Which is higher, the Eiffel Tower or the Shard? No phones, no Wikipedia. Do you think it's A or B? You may not be sure, but how confident are you in your answer? Have you thought of that? And have you put a note in your number, no cheating to yourself, number in your head? Okay, which is it, do you think? No, it's A. The Eiffel Tower is higher by only just. Right, if you said 10 out of 10 B, you've got off to a really bad start. You really have. It's going to take a lot of making up if you've said 10 out of 10 B. Okay, who's older? The Prince of Wales, William, or the Princess of Wales, Kate? So you've got to guess. Not guess, you might know. It's great if you know. You're going to get lots of points. Well, not that many. Okay, any idea? Okay, and you've done your judgment, and the answer is? B. Yeah, she's 6 months older. So you may have picked up a few there or not. Okay. Which was founded first, the Royal Society or the Royal Institution? A or B? And how confident are you in your answer? Okay. Some people should know this. I hope. And the answer is? A. Royal Society was founded first, 1660, 1799, so only about 140 years difference. Okay, right, 2 more questions. Which is furthest west, Bristol or Edinburgh? Which is further west, Bristol or Edinburgh? And how confident are you in your answer? Okay, have you thought your answer? And the answer is? B. Yeah. Yeah, I know. Yeah, okay. If you said 10 out of 10 Bristol, another bad start, okay. Right. Finally, I mean, these are pretty arbitrary questions, you must admit. In what years did Mick Jagger study at LSE? No, these are important questions. Come on. 1961 to 63 or 65 to 67? Shh. Have you got made your judgment? And the answer is? A. Yeah, 61 to 60. And then he left because he was going to stay. He was studying until he got a recording contract, and then he left. Okay, so have you got a rough idea of how many points you got? Come on, who got positive points? Oh, not bad at all. Did anyone get quite a lot of points? Did anyone get sort of more than 60 points? No, anybody? Is there somebody there? Oh, wow, 59. So people got more than 50 points? Well, that's pretty good. That's pretty good. Was anyone quite cautious and stayed with 5, 6, and 7s and stayed near 0? Yes, yeah, there are some. Good, yeah. So the point is, the first group are either lucky or they know people who know something. And the second group are people who know they don't know something. There is a third sort of person who think they know things and don't. And they tend to get rather large negative scores. Okay, did anyone get less than minus 50? Yeah, anyone less than minus 100? Below minus 100? Oh, there's some, yes, that's what we like to see. Do not have these people as your financial advisors. So, I mean, I love these things. But the point is that these techniques are serious. I mean, this can be like a bit of a game. It actually makes quite a good game show. But these are serious points that are used to train people not to be overconfident. They're used to train intelligence analysts to kind of know what they don't know. And it's the scoring rule that's used for super forecasting competitions, where people are putting probabilities on events that might happen in the future. And they use this scoring rule in order to penalize people. Oh, yeah, mathematics. What's the pattern in the scoring rule, in the score? What's the pattern in that score? Anyone see it? So it's a really rigorous mathematical pattern that's carefully designed to maximize so that you maximize your expected score by being honest. Okay, so let me give you a hint. If you think the most you can get is 25, so if you subtract 25 from all those numbers, you get the amount you're losing by not being absolutely correct. So subtract all scores from the maximum 25, and that's the pattern you get. What's the pattern? They're the squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. It's squared error loss. You're losing the square of your error. And this was developed in weather forecasting by Breyer, weather forecaster in 1950, and is used to assess the quality of probabilities of rain. Has been for 70 years. That's the rule that's been used to assess probabilities of rain. So it's got some very nice mathematical properties. Okay, so it's a serious thing. So although these numbers might appear just come out of thin air, they come out of your mind, they're serious numbers that we can check how good they are, and we can find out who among you, would do better, and we could train you up. We could really train you up. So I'm going to jump subject rather into luck, although I'll come back to the probabilities later, because I feel luck is very important. Luck is a form of a way we deal with uncertainty. It's the operation of chance taken personally, a definition that David Spiegelhalter uses, who wrote a book on luck. And the idea is these are things that happen. When we talk about luck, it's when things happen to people, yourself, that are unpredictable, that are not in your control, and yet have an impact on your life, either positive or negative. Now, I don't think of luck as some external force that's operating on you. What I'm meaning is that these are things that retrospectively, looking back, we can say, oh, that was lucky, or that was unlucky. And very often that's as far as people get. They just, oh, that was lucky, that was unlucky. Well, no, but philosophers have deconstructed luck. And I think this is a really powerful insight. And I personally relate this to my grandfather. There he is, Cecil Spiegelhalter. At that point, he was Sergeant Spiegelhalter then. And he was born just in time to go into the First World War. And then he had the really ill fortune. He became, commissioned as a second lieutenant, and he was given the great job of brigade gas officer in the Ypres salient in January 19, just after the Battle of Passchendaele. He had to do an exam. To do an exam for a job which must have had a life expectancy of about 2 weeks does seem slightly unfair. And he passed his exam. I wish he had failed. Never mind. He passed the exam, and then he had to, in landscape like that, he had to walk around the trenches inspecting gas facilities. And he kept a diary, probably illegally, which we've got, beautiful volume. And it's full up with statements like, desolation, narrow escape, lucky to get through in time. And he lasted 3 weeks in the job, which I thought was pretty good going, before he was blown up. He lasted 3 weeks, and then he was blown up, coming back from Eagle Trench and Bear Trench, which I visited. And now, was he lucky or unlucky? Well, I'm here. So you can tell he was quite lucky in that it didn't actually hit him. But he got disordered action of the heart, was in his soldier's heart, and he was invalided out, or declared B2 out of the front lines, which meant later on his battalion was sent to a quiet sector, which at that time in March 1918 was the Somme, which was just in time to meet the Kaiser's offensive, 1 million German soldiers. And his battalion, we've got the movement records, had to go over the top twice. And by then he was second lieutenant. He would have had to be first up the ladder, blowing his little whistle, and I wouldn't be here. Absolutely, almost certainly. So he was actually very lucky. And what he illustrates there is, I think, types of luck, which philosophers have identified. The first is constitutive luck. Now, constitutive luck is it's the most important type. It's who you are. You know, when in history you were born, who you were born to, the thing over which you had no control, your genes, your parents, your environment you grew up in, the time of history, etc., etc. You didn't choose to be born. You know, there you were, and you have to take what you're given, but it's incredibly important for the whole of the rest of your life. And then he had the bad constitutive luck of being born just in time to go into the First World War. And then circumstantial luck is being at the right place at the right time or the wrong place at the wrong time. He had terrible circumstantial luck of being brigade gas officer in the Ypres salient in January 1918. He was blown up January the 29th, just yesterday. But he had fantastic, the third type of luck is outcome luck, or you might call dumb luck. It's just how it just happened to work out at that time for him. And for him, it worked out okay. And I really like this deconstruction. I think it's really valuable. He lived till he was 81. Now, as another example of this, I'm not old enough to remember this one, but this is the plane crash when DC-3 Dakota flew into Saddleworth Moor in 1949, killing nearly everyone on board. And on that flight was my friend, Professor Stephen Evans. Just gave evidence to the COVID inquiry last week. I've worked with him on lots of inquiries. And he was great. And he was on the flight. One of the few, as a young boy, one of the few survivors on the flight. So what was his luck? He had terrible circumstantial luck of just being on that plane at that time. You know, no control over it. He got onto a plane that was going to fly straight into a moor. Okay. He had incredible outcome luck of being, so he had bad circumstantial luck, brilliant outcome luck of actually surviving. So what was his constitutive luck? How did that come into it? Well, his father had been in the RAF and knew that the safest part of any plane was at the back. So he always made his family sit at the back of the plane. And it was only people in the back row who survived. So, in fact, though, Stephen's younger brother was killed in the crash. So it was a terrible tragedy for everybody. But he survived. So he's quite ready to just admit this was an extraordinary event. Now, constitutive luck, as I said, it's who you're born as. That's what I want. Who you're born as, and I think the phrase that comes out very naturally from that is sort of making the best of the hand you've been dealt, because you can think of who you're born as the hand you've been dealt. You didn't give any, you didn't have any option, you didn't have any choice. It's just that's who you ended up being, and we should point out, I think it's a really good analogy, because we are all genetically unique in our little ways. We all are genetically unique, absolutely unmatched. And I think it's not genuinely realized that every shuffle is almost genuinely, certainly unique. So when I shuffle these cards, which are well shuffled, I can be incredibly confident that no one in the entire history of humanity has ever had the cards in that order before. I'm going to shuffle them again. And I am unbelievably confident, I bet you all the money in the world, that no one in the entire history of humanity has ever had a pack of cards in that order before, shuffled them into that order before. And that's quite difficult to believe somehow. I think I find that later on I'm going to do some things where things that you might think are rare are actually quite common. This is something which people think it must be quite common and is actually staggeringly rare. Now, it's quite difficult to prove, because I can't prove you that no one's ever done that shuffle before. I can't say logically they haven't. But statistically, that is the most likely result, because we just have to count how many shuffles there are. And if you think of how many shuffles there are, the first card can be any one of 52, and the second card can be any one of 51, and the third card can be any one of 50. And so it goes on. If we look at all the different combinations we would want, and we get to that, which is known as 52 factorial, and that's a really big number. I'm not suggesting you do it, but if you've got your little calculator on your phone out, started tapping it in, the numbers would soon go off the top of the screen. And after a while, your phone would explode. Really. Do not try it. Do not try this at home. It's really dangerous, because it's a very big number. It's a really big number. Actually, it's a bit bigger than that. Yeah, it really is a big number. Oh, it's bigger than that? Yeah, no, it really is a very big number. Oh, I forgot some zeros, that's it. Is that. It is staggeringly large. I think it's 68 numbers, 10 to the 68 or something like that, which is a staggeringly big number. It's about the same as the number of atoms in our galaxy. That's why I can be confident that no two people have ever shuffled the cards into exactly the same order. I still find it really difficult to believe. It's just not intuitive. But I do some sums in the book. So if everybody who'd ever existed in the entire history of humanity had done nothing in their lives but shuffle cards, the chance that any two at any time would ever have done the same shuffle is about 10 to the minus 19, which is, I don't know, billion or something like that. So unbelievably unlikely. So that's really difficult to comprehend, especially as I can't prove it, of course. But it is just staggering. Okay, so sometimes, though, we can do something. We talk about luck. Okay, I want to show you another example of luck. Here's Darren Brown. You remember Darren Brown? He's a great, illusionist. And you may have seen this program on years ago. I just want to show you a couple of clips from this program. So what he's going to do, and what he said he's going to do...
Side and tails on the other. But I want you to watch this and try and work out how it... Thank you very much indeed.
Okay.
I'll show you later.
How did he do it? Sorry? No, it's a real coin, and that was a real flip. Those were real flips. No, several takes. Yeah, possibly, yeah. Okay, yeah, I think some people will have a go. Those skeptical people in the audience are disbelieving of something. Yeah, okay, so he flipped 10 heads in a row. Was he lucky or unlucky? So, okay, let's show you another little minute of clip, how he did it.
10 heads in a row.
There's a couple of things like, what a professional. Really, after 9 hours to make it look like it was his first time. That is really extraordinary. But the crucial question for me is, was he unlucky or lucky to take 9 hours? So who thinks he was lucky to only take 9 hours? Okay. Who thinks he was unlucky to take as long as 9 hours? Yeah, you're right. Okay. The probability that he succeeds at any particular attempt is, as he said, 1 in 1,000, a half times a half times a half, 10 times. So on average, we expect to take about 1,000 attempts, but a huge spread around that average. I reckon by the time I timed in how long he did the flips, and so I think he took about 1,600 attempts. So he took more than the average number of times it should take. So he was unlucky to do it. He was unlucky to take so long. My colleague, James Grime, repeated the feat, and he did it in an hour. It's all on YouTube. It's the dullest YouTube video you could ever watch. I don't think he gets many likes on it, to be honest. But there it is, him flipping away for an hour, and he got 10 heads in a row after only an hour. And we can do the sums on this because the waiting time before an event like this is called follows what's called a geometric distribution. So this is a geometric distribution with mean 1,024, and it shows that the probability of getting it the first time at the first attempt is 1 in 1,000. And then the probability of having to wait even longer goes down, because if you have to wait till 1,500 attempts, you'll have failed 1,500 times. And so you have to take that into account. So, and in fact, out of that distribution, we see Darren Brown was way out in the tail, and James Grime was actually very lucky to only take that long. So we can sometimes quantify, if we know what's going on, just how lucky or unlucky somebody is. And the other way in which we can do some quantification is in coincidences. So, I think, why do they happen so often? Why do they never happen to me? I'm hopeless. Because I realize that for a coincidence to happen to people, you have to notice things. And you have to talk to people to find out that they went to the same school, or their brother knew somebody or other. So, and I never talk to anybody or notice anything, so they never happen to me, but they happen to other people. It's really exciting. But look, this happened to me. I bought a box of eggs, and they all had double yolks. That's why it's on the front of the book. Double yolked eggs. So, and the man from the Egg Council said that there's only 1 in 1,000 eggs are double yolked. So this looks like a 1 in 1,000, 6 times 1 in a million event. So, wow, isn't that amazing? I'll show you later how I did it. Yes, how I did that trick. So birthday coincidences happen a lot, and it's a fairly standard thing. But as I've got a lovely audience here, I'm going to try a bit with some of you. So the point is, you probably heard that if you've got 23 people, there's a 51% chance that 2 share a birthday. 35 is 81%, and you've got 80 people, they're nearly absolutely certain that 2 will share a birthday, even though it's way less than 365. And some people find that quite unintuitive, and so I'd like to just show some ways in which you can think about it to make it, I hope, slightly more intuitive and even do some sums. So warning, maths! Now, when I was young, they always used to announce that those of a nervous disposition may wish to look away now when they were going to show anything nasty on television. So if you do, but I thought, come on, this audience, I normally take all the maths out of my talks, but I thought, Christ, no, I'm going to put it in. So there, tough luck. So imagine how do I get to that 51% chance? First thing. So imagine 23 people all in a row. I'll do it in a minute. I'll try it on 23 people. The first is some birthday. It doesn't matter what it is. But what I do, and this is always a trick to do this, is to work out what's the probability that there's no matches. So you work out the opposite of what you want. That's the easy probability to get at. The probability that there's no matches, which means that the probability to do that, the second has to have a new birthday, a different birthday from the first, which is probability 364 over 365. And the third has to have another new birthday that hasn't been taken so far, which is 363 over 365. And the 23rd has to have a new birthday, and that's the probability you need. And you multiply, so the probability they all have different birthdays is all those numbers multiplied up together, which comes to 0.49. And this is where the lack of intuition comes, I think. The fact that you've got 22 numbers there, all of which are quite near 1, but when you multiply them together, they go below a half. And that's why we find it so difficult, I think. Because each separate event is actually quite unlikely, but put them all together and it becomes quite likely, because 1.49, so the probability there's at least one match is 1 minus that, is 51%. So that's a very clumsy way to do it, and I'll show you a neater way in a minute. Okay, so trying to make this a bit more intuitive. If we think of 23 people, I've got to find 23 people. Hang on. 6, 8. I'll do it on this side. I think it's easier. So we've got 2, 8, 12, 15, 18, 20, 23. Oh, that's great. First 4 rows has got 23 people in it. Don't do anything yet. I'll come back. I'll try to do 2 tricks at once. So 23 people comparing the birthday. If you all got up and tried to shook hands with each other, there would be 253 handshakes. There's 23 people shaking hands with 22 others, but that's counting each pair twice, so that's 253 possible handshakes. Now, each of those, if you think of that's the number of pairings, and the probability that that pair has the same birthday is 1 over 365, so the expected number of matches is 253 over 365, which is 0.69. The fact there's some dependence between those events doesn't matter when you're calculating the expectation. So I expect on average among you lot 0.7 matching birthdays, which is a slightly odd thing. But how does this help us get the probability of a match when we know that there's 0.7 matching birthdays? This is the trick. Extra warning, even more difficult maths. So, hold on to your hats. Look away now. Look away now. This is a useful rule that I use all the time because I can almost do it in my head. This means, suppose there are many opportunities for a particular type of rare event to occur. And we expect on average m of these things to occur. So some notation, little one, rare events. The chance that none of them will occur is approximately, or even exactly, e to the minus m. Now, e is the exponential constant, or Euler's number, 2.718, whatever, which I'm not going to try to explain. I'm sure there's some math teachers in the audience who just love to explain e to you, but I've tried before, and it's absolutely doomed. So, it's on your calculator, to be on your phone. That's all you have to know. So suppose each, and just to prove that, suppose each of n independent rare events, so really independent events, had a small probability p of occurring. So we expect n times p to occur. The chance that none occurs is 1 minus p to the n, because the chance that any particular event doesn't occur is 1 minus p, and we multiply that up n times. So we can simplify that. We can write that as 1 minus np over n to the power n, which is 1 minus m over n to the n, which is approximately e to the minus m from the definition of e. Now, I told you, I warned you, don't complain. I did warn you, but people who have done this will recognize it, and I hope rather like to see it appearing in this context. For dependent events, like birthdays, because they're not all independent, we can assume the number of events has approximately a Poisson distribution. This is the Stein-Chen theorems, which I'm not going to go into. So the probability of 0 events is e to the minus m from the Poisson approximation. Now, you can now, having done that, you can now look back. So this makes things really easy. So we've done all this. We got expected number of 0.69. So that means, using this useful rule, the probability of a match, of no match, is approximately e to the 0.69, which is 0.5. I mean, exact is 0.49. 0.5 is not bad. So around 50% of a match. So you can do almost all, you can do all of that really easily on your calculator without multiplying together all these numbers, if you want to. So in the women, just to demonstrate this, in the Women's World Cup, in a World Cup squad, there's 23 people in a World Cup squad. There's 32 squads, each with 23 members. Let's see if this works. We'd expect about half of those squads to have people with a matching birthday. There were 17 squads, had at least one pair with a matching birthday, and some with 2 pairs, and 2 with 3 pairs. And there was a lovely example this was, here we are, this was the Nigerian team, which had 2 players, both born on Christmas Day, and there was Christy and Glory they were playing, both members of the squad, both born on Christmas Day. Isn't that lovely? That's a really nice example. Okay, so another example of the useful rule, which I find quite easy, is, you remember I did ask you about the last 2 digits of your phone number? You had to fill that in coming in. So 23 people comparing the last 2 digits of their phone number. There again, 23 times 20, there's 253 handshakes there. But the probability of any pair matching is 1 over 100. So now we expect 2.53. In any 23 people, we expect 2.53 matches in terms of the last 2 numbers. So the probability of no matches is e to the minus 2.53, 0.28. 92% chance of a match. In fact, 94% chance of a match. So if you've got 23 people, it's almost certain that 2 of them will have the same matching number on the end of their phone number. Let us try. Okay, I've got 23 people, unwilling subjects here. So what I'm going to do, you've already filled in a form, but I haven't got them. So could you just shout out your birthday, month and day, and the last 2 digits of your phone number? And if anybody up to the first 4 rows hears their birthday or their the numbers, please put your hand up so we can finish quickly. Right, your birthday and your number.
November 18.
And your phone number?
77.
77.
February 27th, 76.
Whoa. Okay.
October 7th, 02.
02.
October 31st, 36.
October 31st, 36.
February 3rd, 51.
February 3rd, 51.
June 27th, 97.
June 27th, 97.
June 3rd and 1-1.
1-1.
August 13th, 7-6.
Yeah. Oh, we got 7-6. Right, we did it. Right, okay. So we got the two phone numbers. Let's go. Okay. As I said, it was certain this was going to happen. Pretty certain. So that was completely. So that's it. That's quite good. Not bad. Oh yeah. Okay. Good. Thank you.
February 1942, phone number 33.
3-3, 15th Feb. Let's see if we can get a birthday. Only 50-50 chance there. Yeah.
Number 1,
Yeah.
7-3.
7-3.
March 20th, 7-5.
7-5. Great. 7-5. Almost sitting next to each other. Pretty damn good. Okay, so we've got two pairs. I expect 2.2.5, so I expect 2 or 3 pairs here. Yeah. Okay.
January 2nd, 18.
Yeah.
November the 11th, 75.
November 11th, 75.
March 24, 6-3.
March 24, 6-3.
May 26, 37.
3-7.
July 27,
And then the phone number?
63.
63. We got another 63. Did we have a 63? Yeah, okay. 3 pairs, not bad.
16th of July and 6-0.
16th of July, 6-0.
November 3rd, 52.
November 3rd, 52.
23 of January and 48.
23 January, 48. Yeah.
26th October, 0-1.
01.
1st of February,
09.
09.
July 25th, 24.
31st of August, 12.
31st of August, 12. Okay, so I didn't get a birthday. Well, it's only 50-50. It's like flipping a coin. Come on. That was, yeah, I mean, so it's not amazingly lucky. 3 pairs. Not bad at all. Thank you very much, Steve. So let's see. I want to see if the goddess Fortuna, because when you came in, you filled in a little form with your birthday and the number, and you had a group, and each of these groups got 23 people in it. And then 19, you comprise here 19 groups, so you're scattered all over the place, 19 groups, each with 23 people in it. So the last 2 digits of their phone numbers, there's a 94% probability of a match. Birthdays, 51% probability of at least a match. So randomness is clumpy. So this is what I expect to happen. So I can calculate that out of these, what I've got here, the number of groups with a matching birthday and the number of groups with the matching phone numbers. Okay, and I expect for the birthdays, on average should be about 10. If I'm lucky, it'll be higher. I'll let you know. But for the phone numbers, I expect nearly all the groups to have a matching phone number. I'll be really unlucky if it's not. So let's see what I've got here. I haven't seen this. Okay, here we go. 1, 2, 3, 1, 2, 3. And I got birthdays 9. Oh, not bad. And phone numbers 18. Okay. The goddess Fortuna was shining down upon me. It just says it works, it works. And one final little thing I want to do, just to see what's in. So there's 400 people in here about. So have I got time for this? Yeah. Could you just turn to your neighbour and just say your birthday and your phone number on both sides, and then just make a mental note if you're exact match or one out. Okay, so could you just do that, please? Okay, have you done that? Have you done that? Okay. So what I'd like to know, first of all, is anyone sitting next to someone with a birthday 1 day out? I can't see anything. I can't see the lights. There's a pair there. Well, and you're just 1 day difference. I'm expecting 2 pairs. Come on, there must be some more. Another pair there. Any more up there? No. Oh, there's 3 pairs. Okay, that was quite lucky. So I expected 2 pairs around. Okay, there should be, I expect 1 pair in the audience who's sitting next to someone with exactly the same birthday. Is there anybody here? No? Oh, no. No, the goddess Fortuna was not quite shining. Okay, this is easier then. I expect, 4 pairs of people who are sitting next to each other with matching phone numbers, last 2 digits. Where are they? Okay, who's got the same phone number, last 2 digits? How many have you got? 2 there? Any more? Any more? Any upstairs? Oh, dear. Dear, dear, dear. You haven't shuffled yourself around properly, have you? Honestly, you'll all have to get up and come in again. That was not very successful at all. Never mind. Okay, it's not bad. So the point is that we can, and it's actually with 20 people, there's an 87% chance. So if you ever want to make money off anybody, just get 20 people together and say, I bet 2 of you have got the same last 2 digits of your phone number. And you've got an 87% chance you'll win. So just now coming, nearly finished now. This, I think, is great. This is a game, Trays, from 1713. It's great. So this is a game they used to play where one person would have all the clubs and one person would have all the diamonds, and then they'd play snap. They'd turn them over one at a time, and somebody would win if they turned over the same card at the same time. They both turned over the 5, both turned over the 6. Who thinks it's more likely to get a match that will be a snap than not a snap? Who thinks it's more likely there'll be a snap than not a snap? And who thinks it's more likely there won't be a snap than there will be a snap? Yeah? No? Okay. No, they're actually, no, it's a 63% chance of a match, 1 minus 1 over E. So actually it's always more likely there will be a match. And the really interesting thing, I think, is that it doesn't depend on how many cards there are. So you can play with a pack of cards each and flip them, turn them over, play snap, and you get a snap if there's the same card as turned over. It's still 63% chance you'll get a match. And that is, I find, not very intuitive. You think, well, you know, what's happening? It works down to you only need about 5 cards each, and it's a 63% chance there'll be a match if you flip them over. So it's a good game, again, if you want to make money. Just however many cards you got, just say, okay, I win if we both turn over the same card. And it's a 63% chance, no matter how many. So the useful rule says the probability of no matches is approximately e to the minus 1 is 0.37. Because no matter how many cards there are, the expected number of matches is always 1. Euler did this in 1753. He did the exact calculations for this. Quite extraordinary. Anyway, so there's another, you know, it shows that probability is not intuitive. It is so unintuitive. It's untrue. And I believe, personally, the reason it's so intuitive is that we just made it up. Okay, so how did I get 6 double-yolked eggs? I bought a box of double-yolked eggs. So, again, very rash to trust me, you see. So, and actually, it's not difficult. Look, you go into, there are Waitrose, £3.80, double-yolked eggs. Tesco's only £2 for your double-yolked eggs. So, you know, the 1 in a million is nonsense. And I think I've just about got time now to show you. So can I show you? Yeah, I got 4 minutes left. Yeah, okay. I want to show you about when I did Wipeout. Now, do people recognize this? Yeah. So this is in Argentina. It's an idiotic obstacle course you go over. And I'd done some analysis. I got on the game and I downloaded all the data of the previous matches and plotted all in R. And you have to go through the first... there's 20 of you, and if you get through the first 12, you go on to the next round. And I worked out what time I'd have to need to qualify to get to the second round, and I realized I had to get through in 3 minutes. Okay, so this is how it went.
Wow! This first ski lift.
Well, so statistics didn't completely get me through. Thank you very much.